How's it going, everybody? My name is Antonio, and you're about to watch, listen, or just, leave the computer running while you do the dishes and you're not really listening to a program that is general and impersonal in nature, one that will include a lot of forward-looking statements and speculations about future events that may or may never take place in the future. But it's also going to be a conversation that will not include any financial nor investment advice whatsoever. So please do proceed with caution. This is for your own good. Do more research before trusting talking heads on the internet, as I've heard most people who do that, especially in this sector, end up losing money and eventually brain cells too. And today that's strongly used here. You're really going to be talking about alternative forms of nuclear energy, so fusion, molten salt reactors, thorium, SMRs, whatever may have you. And we're going to be talking about, you're going to be talking about where we stand now. Will they work? Do they work? Does that change something for the uranium investment thesis and stuff like that? Before we get into it, though, there's a question that I've been sort of having myself, and I've seen this discussed by different people on Twitter, but I don't know really who to trust. And given your background and education in nuclear engineering, I thought I'd ask you, because you've been also 50 years in the sector, so. I don't know, you probably started studying atoms right out of the womb or something to get that much experience looking at you. But so do you believe that we need an energy mix? Like, do we need wind and solar and whatever else unicorn farts people want to keep coming up with? Or would you like, do we need that? Or could we just go like 100% nuclear? Could we go 85% nuclear? Is that doable?
Yes, it is. I'd say 20 years ago that was um, less likely than now. Nuclear power plants, the current versions that we have, the 1,000 megawatt machines, are very large. They're also very expensive. So when you have a machine like that, you want to run it at nearly 100% capacity factor. You want to run it all the time because you make money when the turbine runs. You don't make money when it stops. So when it's running at low power, you're not. It's pretty obvious to most people, but that's a big cost impact to the operators of nuclear generating stations. For organizations like EDF, I should step back a bit here, to show that it is done and it is possible. EDF in France actually does this already. They've been doing it for years because their nuclear capacity is 70% of their total grid capacity. So that's way above France's base load. So the French nuclear power plants have been operating this way for a long time. Now EDF is a French nationalized company, and their job is to produce electricity for France, and which they do a fantastic job. But they are able to absorb those additional costs of running nuclear power stations at less than 100% power output. That's the reason why it's not done. It's not that it's not possible. It is very possible. Pressurized water reactors can do it. Some CANDU reactors can do it. There are technical difficulties in doing it. It's very expensive on fuel, for one thing. So there are costs in doing it, but it's a cost issue. It's not a technical issue. And there's a big difference between the two. So when you have a high nuclear component in the grid, as the France does, 70%, you have to run some of those nuclear power stations at less than 100%. And that costs money to do that. It's costly in terms of less power output for the investment you made, and it uses up fuel. It needs a different fueling regime in order to do it. The French do it very cleverly. They are very ingenious at what they do with the fueling of those reactors. But yeah, it can be done. So technically 100% is perfectly feasible. The purpose of a grid is you draw power off the grid. So when you draw power, when you switch on an electric light bulb somewhere, there's a generator somewhere that's producing that electricity. So when you put a 100-watt light bulb on, well, not nowadays, but let's say you put an electric heater on a kilowatt. Some generator somewhere is now demanding you put 1,000 watt demand on that electric generator. So the grid is a collection of electric generators. When you draw power off the grid, you are trying to slow down an electric generator somewhere. You're putting a load on it. So it's just like a car. You put a load on it, it slows down. It's exactly the same, except it's electrons that move about, not wheels. So when you draw too much power off the grid, the voltage in the grid starts to drop, and there are limits, design limits on the grid of plus or minus 6% on the voltage. So, everybody's used to 110 volts. I'm not sure what Europe uses, but, they're 110 volts in North America. That voltage is what governs every electrical piece of equipment in your house. If you change that voltage, all of that equipment starts to go wrong. So there are limits. Plus or minus 6% is the general rule of thumb on the grid. So if you put big loads on the grid, you will drop the voltage down and things will go wrong. So when you draw electrons off the grid, there have to be exactly the same numbers of electrons going into the grid that come out. It's that simple.
Okay, so grid could be an issue.
But
if you go 100% nuclear, grid could be an issue. But France is also struggling with other issues.
Right.
I mean, if you
just hold that thought a minute.
Sure.
You can run the grid at 100% nuclear. It's not easy to do it, but it can be done, even with large power plants. However, with small modular reactors, it is a whole lot easier to do that. Because small modular reactors are a lot more flexible than the big power plants are. So the nuclear of the future, as I envisage it, and I think many grid operators envisage it, is large nuclear power stations sitting on the grid as base load, which gives you the reliability, coupled with small modular reactors, which can more easily load follow than other reactors can. Depends on the design. There are hundreds of designs of these, by the way. It's not just one design. Some prominent ones now, but there are literally hundreds of designs of SMRs out there. So some of them are really well suited to load following, very well suited to load following, molten salt reactors being one of them. So they can follow the load on the grid up and down all day long, and really not much better than large nuclear plants can do. Large nuclear plants are designed for base load. That's what they were designed for. It's like Ford. You build a power plant, to make X thousand vehicles a week, and then somebody says, don't need that, need half that number. Well, you've still got the plant and the factory and everything else to pay for. So it costs you money when you're not running it at full capacity.
Right.
Because the price of cars goes down the more you make.
Right.
Same with electricity. It's no different.
I definitely want to go back to SMRs, molten salt reactors, and all that. But it's interesting that you mentioned exactly France, because France's cost of electricity, per megawatt hour is one of the highest in Europe now. Has been going up because they've been having problems with because of the drought. So some of their rivers weren't, large enough for them to run the power reactors. They were also having troubles with some maintenance works that had to be done. It seemed like they mismanaged it there. And because they were relying that much on one source of energy, that sort of, shot them in their leg, so to say, and it had their cost per megawatt hour going up. Why did that happen? How do you see that issue?
Oh, France has been having a lot of problems lately with their fleets of reactors. When they built them in series. So they built all of one set of reactors exactly the same, which is great from a mass production point of view. But it's not so good when something goes wrong, which you didn't anticipate. They've had a lot of corrosion issues with some parts of the plant. And of course, if you've got a corrosion issue with one plant, now you've got the same issue with all of them because they're the same. So I think they have 3 series of reactors in France. So the earlier series has these corrosion problems. So that's one of the drawbacks of doing it. But those are resolvable, and they are resolving those issues. Did it hit them all at once? Yes, it did. And nuclear is very highly regulated, so you're not allowed to run reactors when there's any kind of a problem with them. So in the French regulator said, well, until you fix this, you've been a problem. You have to shut them all down, which is a problem. The issue of water levels is a very interesting one. A lot of the French nuclear plants are on their large rivers. They're on the Rhine and the Rhone and other rivers that run through France. And their water levels have been very low, which means they can't get the cooling water to the power plants. Most power plants have cooling towers, which alleviate that problem somewhat. It means the cooling towers weren't big enough to handle the entire cooling load. So in Ontario, for example, where I am, all of the power plants are on the lake, either Lake Huron or Lake Ontario. So they draw their cooling water from the lake, and the lake level does go up and down, but they draw it from the bottom of the lake, right underneath the lake. So the tunnels that go out underneath. So, it's something they didn't ever anticipate is these low water levels, but, it's the fault in the design of the reactor, really. They shouldn't have used that cooling system setup. They probably should have gone to larger cooling towers or more of them. So when you have a plant built inland, you need cooling towers. The reason you need them is to cool the generator down. It's the turbine. When the steam goes into the turbine, it goes through a series of blades, just like a gas turbine. Once it gets to the end, it's still steam. We can't put steam back to the boiler. You have to put water back to the boiler. So you have to condense the steam. And the ways of doing that are either with cooling water, cold water from lake or river, which condenses the steam back to water and it's pumped back to the boiler, or you do it with cooling towers. And many plants in the States use cooling towers, the inland ones, and some use a combination. They'll use the river or water body as one source of cooling, and they'll also use cooling towers. Some plants use all cooling towers, for example. So it's a question of the design probably didn't anticipate low water levels.
I guess that's sort of the argument that people are having, or at least the ones that I'm reading on Twitter, is that if you rely too heavily on one source, you're always going to have some type of an issue, something unforeseen, some kind of a design fault, as you said, or something, whatever it might be. I don't know anything about those, but it could be anything. Could be stuff that we're not even thinking about right now. So that risk, it has to get taken care of, I guess, and that's why people are opposing 100% nuclear or a high percentage of only one source of energy, I guess.
It's a consideration. Yeah, I would agree with that. Do things go wrong with nuclear power plants? Yes, of course they do. They're a very complex piece of equipment. They're designed to the nth degree of quality, but that doesn't mean to say things can't go wrong, and they do. I've seen it many times over my career where unanticipated things have occurred. The designers didn't think about it, or should have thought about it and didn't. Many different things go on. So I suppose on a philosophical point, relying on just one source of energy is probably not a good thing to do. But the issue is not the energy source, which is splitting atoms. The issue is how you do that. So if you're relying on just one design of reactor for all of your 100% capacity, then that could be a problem. If you get a design fault in that reactor, then you've got to shut them all down. That's a big problem. I see that. And it's a very valid issue. The solution, of course, is don't rely on one design. Have several different designs, then you won't have that problem.
Right. That's maybe a good segue into what I really wanted to talk about today, because what you said so far, I guess, makes sense to me. But I see all these different types of nuclear energy that claim to be it. They've solved one large issue, like they've solved the waste issue or whatever it is. They try to solve one of the main problems, I guess, that people throw around nuclear to have, even though they're not that big of problems if you go looking into them a little bit more in depth. But look, the thing is that the golden retriever that I am, I get excited about all of them, and like I want to throw the very, very little money that I have left, I want to throw it at them. But after my uranium fiasco, I thought I'd wait, I'd slow it down, get extra opinions, and I want to start with something that has been in the news as of recently, and that's fusion. That's what you mentioned at the beginning as well. I read an article recently that said that fusion is basically nuclear power, but without the risk of the meltdowns, and there's no radioactive waste. So that's sort of how it's being advertised. And you know, it was all over the news recently, and the title said that it was the articles basically said that it tested something successfully for the first time ever, but it's not, it was rather small scale, and it still had to, it still had to be developed, but it's also decades away, they said, probably. So what exactly is that fusion? Tell me a little bit more about it, and are you interested into it at all?
I did a lot of work on fusion years ago when I was in England. There's two ways of getting nuclear energy out of the nucleus. Energy comes from destruction of mass. It's E equals mc squared. That's where the energy comes from. If you weigh the fissile isotopes after you split them and before you split them, you'll find a very, very tiny decrease in mass. And that comes from E equals mc squared. There's two ways of doing it. You can either split atoms apart, which is what we do. We split uranium-235, and we get energy out in the form of high-speed neutrons, fission products, and other things. And they, in the nuclear business, is a very well-known curve. It's called the binding energy curve, and it's shaped like, if I can do it backwards, like that, and it goes down slowly like that. And the vertical axis is the amount of energy you get out from splitting atoms, and the vertical part of the curve is getting the energy out from an isotope of hydrogen and tritium, which is another isotope of hydrogen, and you force them together, you will get energy out, a lot of energy, and you do not get the radioactive byproducts because you're forming helium. So when you jam these two nuclei together, you make nuclear energy, a lot of it. And that job is extremely difficult. It is not easy. And anybody who thinks this is a simple job is very much mistaken. Fusion is not going to occur tomorrow. There are two ways of doing it. One is to make the nuclei, the deuterium, the tritium nuclei, move so fast that they smash into each other and fuse. Or you blast them with laser impulses, which jam them together. It's the same thing. What they've done recently, laser technique, which is very than it is, or to convert it into a commercial power station, than it is for the other way, which is magnetic confinement, because the temperatures you have to get up to are hotter than the sun. So there's no material on Earth that will withstand it. So you have to confine it in a magnetic field. It's in a torus. They're called tokamaks, which is the Russian word for donut, torus. So you have to get this plasma, which is no electrons in it, and then you have to have this in the center of this donut, just sitting there on its own, so not touching the walls or anything like that. And then you have to squeeze it with another magnetic field to force these nuclei together. And when you do that with enough force, you can get energy out. That's called the tokamak design, and it is very difficult also. They had not up until now. I mean, you got to get a net energy out. I mean, there's no point in making a power plant. You have to put more energy in than you get out, right? Well, you can imagine that heating up a plasma to, millions of degrees centigrade, that takes a lot of energy. It takes a lot of energy to create the magnetic fields and so on. So that's a huge amount of energy going in, and if you get it going continuously, then you can get a lot of energy out. And at Culham, the nuclear laboratory in the UK, they have achieved that with the tokamak. In the US, they just achieved that with the laser design. In other words, they have this little tiny ball of nuclear material and these massive high-powered lasers coming from all directions, and they just pulse the thing, and they managed to achieve nuclear fusion, which is amazing. I mean, it is a stunning development to be able to do that. But if people think that fusion power is just round the corner, they're sadly mistaken. It's not. It's the holy grail of nuclear energy, of course, because you get a lot of energy out for very little input. And of course, you're not breaking atoms apart. It's the fission products that give you all of the radioactivity and all the stuff that you have to deal with after the fuel is used in a reactor. You can't just stick it in a corner somewhere. You have to contain it. You have to shield it. It's safe, perfectly safe. I've worked in waste plants for years, and it's not a problem. But it's an issue you really don't. If you didn't have to deal with it, it'd be even better. And that's what fusion does. It doesn't produce fission products. Its fission product is helium, which is an inert gas, not radioactive. So it holds huge promise. That's why governments are spending so much on it, because you have no waste. There is some. It's not true to say there's no waste. There is a little bit, but it's not the type of waste material that needs to be contained for a long time.
But so governments are investing in it, but investors shouldn't. I mean, it's too early to even start thinking about it. Is that it?
It's 20 years away at the very least. I mean, kudos to the guys that have done it. I mean, this is a difficult problem they're trying to solve, but it's like, I guess the best comparison is it's like Fermi in the Chicago pile in the 1940s. That's where we are with fusion, and that took 15 to 20 years to get to a commercial nuclear power plant, and certainly not 1,000-megawatt power plant. It's a bit like the Wright brothers flew an aeroplane and then saying that the day after tomorrow we're going to be flying in a 747 across the Atlantic. You have to develop things. Technology takes time, and fusion technology will take time. It's one thing to prove the physics. That's great, and it is a wonderful achievement. But making the leap from there to fusion is at very least 20 years away. I wish it was sooner, but I'm a realist, and it's not.
What about that? What about used fuel reactors? I heard something that the fuel that the enriched uranium platelets that get used in the reactor, they only get used for like 5% or something, but 95% of the uranium is still in there, or the radioactivity. I don't really understand it, but I saw something about used fuel reactors. Are those a thing? Are they closer?
Well, there isn't a shortage of uranium. I mean, the Earth's crust has lots of uranium in it. The material itself isn't that rare in the Earth's crust. There's a lot of it. It even occurs in seawater to about 200 parts per million, I think, or billion. So there's not a shortage of uranium. If there were, then using the fuel again would make sense. I've often written on Twitter that used fuel is not waste, because it has only used a very small percentage of the energy that it has in it. In a nuclear reactor, you have, let's say you've enriched it to 4% U-235. So U-235 exists at about 0.7% when you dig it out of the ground. So the U-308 that you dig out of the ground, the uranium atoms in there, the 0.7% of them, so less than 1 in 100, are uranium-235 atoms. When you put those in, and that's the only one that's fissile meaning that if you hit it with a neutron of the right energy, it will break apart and fission and cause energy to come out. When you put that fuel in a nuclear reactor, of the U-235 atoms, in 100 of the uranium atoms are the fissile one. Now, in a reactor, most of the energy doesn't come from the U-235. It comes from a set of reactions that occur with the uranium-238. when the neutrons come out of the nucleus, they're moving very fast. They're called fast neutrons. They will fission. There's a reaction between uranium-238 that will eventually end up with plutonium-239 and 241, both of which are fissile. So what happens is that most of the energy is being produced by the plutonium out of the U-238, not the uranium-235. Some of it is, but not all of it. So the majority of the U-235 doesn't get fissioned. It stays, it's still in the fuel. Only a few percent of it is actually used up. And most of the energy comes from the plutonium fissions that occur with the U-238. So so when you take it out of the, and I've been asked this question, I wrote a piece on one of the direct message things to one of the guys, and what happens, he said, well, why do you take it out of the reactor? Why don't you just leave it in? Which is a really good question, and the answer is that there's a lot of other reactions that go on inside that fuel, and some of them produce materials that absorb neutrons. So they're like sopping up all of the neutrons out of the reactor, and if you leave it in there too long, there's too much of these materials, and eventually it's called the reactivity of the reactor will go down, and you can't have that. So you take fuel out in about 12 to 18 months in a PWR. In CANDU reactors, they're refueled daily. They push fuel in one end and out the other. Really neat system. But you can't do that with a PWR. So you can't do online refueling, which is online refueling is the better way to do it, but it's quite expensive in machinery and equipment to do that. But it does work. It works very well. So the bottom line is that if you, once you take the fuel out of the reactor, you have plutonium isotopes in it. You have a lot of fission products in it, which are radioactive. And these are fairly long half-life. That's the length of time it takes to decay to half its initial level. So plutonium has a half-life of about 24,000 years, which is what the anti-nukes go on about. But it's what's called an alpha emitter. Very, you don't need much shielding to protect yourself from it. Very easy to protect yourself from plutonium. So that's what happens in the fuel. So when the fuel comes out of the reactor, it has to be cooled because it's hot. Temperature-wise, it's still hot, but it's also got a lot of radioactivity that has to decay away, and it's put in a fuel storage pond. Literally, it's put underwater when it comes out of the reactor and left there to cool down. And then when it's cooled down, after about 10 years or so, they take it out. They put it into longer-term storage. With fusion, you don't have any of those problems. And they're not really problems. We know how to do it. We've done it for years, and it's perfectly safe to do it. Now, you said about using that fuel in a reactor that can burn used fuel, and there are reactor designs that can do that. You're going to use uranium, which is great, recycling and all that. But in order to do it, you've got to cut up these fuel bundles, these fuel elements. And you can't just go and get a hacksaw and chop these things up and drop them in the reactor. You can't do that. It's possible. Not that it's not possible, it is. All things are possible in nuclear, pretty much. It's the cost of doing it. You can buy uranium at $50 a pound, and it costs you, tens of thousands of dollars equivalent per pound to put this other fuel in a reactor that can burn it up. Why would you do that? It makes zero economic sense to me to do that. Great that you can. It could, use up all of the waste fuel, but handling used fuel needs a lot of care. Plutonium itself is chemically toxic. And it has a very long half-life, and it's like I said, it's an alpha emitter, which means it, unless it's behind shielded walls, it can do damage, especially if you breathe it in. So this is stuff that has to be carefully controlled and carefully looked after, and just the costs of doing it would just be prohibitive, in my view, to do that, unless you were desperately short of uranium. And there was no supply of uranium left in the world. yeah, then you probably do it. But otherwise, I can't see the merit in doing it. There's certainly no economic merit in doing it. And there's a lot of hype about the safety of used fuel storage. It's very well protected stuff. I mean, this isn't stuff you just leave out in the yard. That's the way the anti-nukes like to think about. You got used fuel thrown on a big heap in the backyard. It's not like that at all. It's very, very well controlled, regulated to the nth degree by the USNRC and by our regulator here, the Canadian Nuclear Safety Commission, and nuclear installations people in the UK. It's very well controlled stuff. Much more well controlled than coal dust and all the crap you get out of a coal station.
I understand that you have a nuclear engineering degree and all that, but I think you're wrong, because I've been watching The Simpsons, and in The Simpsons, it's some kind of a green goo, and they just put it in a lake. So I'm pretty sure that's how nuclear waste is being dealt with, right?
That's not green for a start.
That's sadly, I watched some kind of a might have been a YouTube video or a documentary that said that a lot of Americans would get their information about nuclear from The Simpsons, and stuff like the green goo in the lake and the all the other issues that come with it. So that's kind of sad. What about thorium though? Some of the issues that you mentioned with the previous two might be solved by thorium, as I'm hearing. Like, they're saying that thorium is closer to being economically viable than fusion is, and then used fuel is. So what do you think about that?
Thorium, the advantage of thorium has advantages and disadvantages, and people will tell you what the advantages are, but they won't tell you what the disadvantages are. Especially those that promote it. Thorium is thorium-232. That's what you dig out of the ground. It is in the form of an oxide when you mine it. The advantage of it is it's 4 times more abundant in the Earth's crust than uranium is. So there's a lot of it, and it's more widely distributed amongst countries. So right now, most of the uranium is in Kazakhstan, Canada, Australia, and Namibia, and Niger, and a few other places. But it's not very well distributed around the world. Thorium is. Thorium exists just about everywhere. India has huge amounts of thorium ore, but well, let me go through the advantages first. Thorium-232 is not fissile. In other words, if you hit it with a neutron, it doesn't break apart. What it does do is it converts itself into uranium-233, which is fissile. So the other isotope of uranium that's fissile is U-233. So it doesn't, U-233 doesn't occur in natural uranium very much. I think there's a smidgen. My physics, I remember physics well, but U-235 is the main fissile isotope that you dig out the ground. So U-233, for all intents and purposes, does not occur naturally. However, thorium does, but thorium isn't fissile. So if you put thorium into a nuclear reactor, you need something to start it. So you would put uranium-235, which is fissile, and produce neutrons. Once you have the neutrons, then you can convert the thorium into fissile U-233. So you can run a reactor on it, that's for sure, and it has been done. There are thorium research reactors. A lot of work's been done on thorium. Not something that's new. It's been around since the 60s, at least the 60s, probably before that. One of the so-called advantages is that it doesn't produce plutonium, which is atomic bomb material. So the proliferation aspects of thorium are much less. It's actually not all that true, because you can make a nuclear weapon out of U-233 as well, and you need less of it than you need U-235. So I'm not sure about the proliferation aspects of it, whether that's a valid point, but it certainly does not produce plutonium. That's for sure. So there's, to that extent, you're not going to produce a lot of material for nuclear weapons by using a thorium reactor. It has, I made a couple of notes here.
As long as those notes are not about how to make a nuclear bomb, because I don't feel like having my window busted by the FBI. So
it's not that easy, believe me. That was the other question I had. What goes in a reactor? People get mixed up about what actually is used in a nuclear reactor. So the fuel pellets, the things that produce the fission, is uranium dioxide, UO2. It's not U3O8, not UF6, it's UO2. And it's sintered into pellets. Sintered meaning they cook it at really high temperatures to make it into these dense, they're about that big. Can you see that? About that big, about ½ inch across. And they're stacked inside fuel pins and then assembled into a fuel element. So it's uranium dioxide that goes in there. Now, uranium dioxide is a very, very poor conductor of heat. That's why they're so small. If they were a good conductor of heat, you'd have big blocks of it. But they're not. They're very small because you've got to get rid of that heat. So the center part of the uranium dioxide pellet gets really hot, a couple of thousand degrees. Well, in accident conditions, it can get that high. Normally, they operate a little bit less than that, but they're quite hot inside. And because the conduction from the center of the fuel pellet to the outside is so bad, I mean, it's like, it's a ceramic. Uranium dioxide is a ceramic material, terrible conductor of heat, probably the worst conductor of heat you could imagine. The uranium dioxide is a bad conductor of heat. Thorium dioxide is not a bad conductor of heat. So you don't have some of the material limitations that you do with uranium dioxide. So it's better from that point of view, better at conducting heat. So it has advantages in the design of the reactor. In other words, you could probably make the thorium pellets bigger. I'm not sure they do, but so it has advantages from that point of view. But it also has a lot of disadvantages. And one of them is that in order to make the thorium dioxide fuel pellets, you need a very much higher sintering temperature. It's something like 2000 plus degrees centigrade. So you've got to cook this stuff really high temperatures to make the pellets, and that's not an easy process to do. We can do it with uranium dioxide. It's done all the time. Just plant down the road from me, in fact, does that. But with thorium, it's a little bit more difficult to make the pellets. Much more difficult process. So it has advantages, but it's the same argument as fusion, and the other alternative nuclear technologies, that while uranium is the price that it is and the availability that it is, there's really no economic advantage in doing it. Now, the Indian government has been promoting thorium for a long time, and the reason is they have no uranium in India, very small amounts. They have a lot of thorium, though. So they have been pursuing thorium design reactors for a long time. Haven't seen any successes out of there yet. And it's primarily because of the fabrication issues. Not easy to make the pellets with thorium. Not as easy, I should say. It's all doable, but whether you want to spend that amount of money on developing a different reactor technology, it's really not worth it. Better to buy PWRs from Russia or the States that you already know, and you have a fuel supply arrangement with them. And that's what Russia does, right? When they sell a reactor, they sell the fuel supply as well, and they get rid of all the waste for you. Big advantage. That's why Rosatom sells so many reactors, because they do the whole shebang. They don't just sell you a reactor and tell you to operate it. They operate it for you. They supply all the fuel, and they take all the used fuel away. What better arrangement can you have than that? That's why they're building them in Turkey. That's why Rosatom has the contract in Egypt, at Aldebaran. So, there are big advantages in setting up contracts like that, especially for nations that don't have the infrastructure like the US does or Canada does.
What about small modular reactors or molten salt reactors in that case? I believe those are molten salt reactors. Aren't those connected? Like, isn't that a part of the small modular reactor or something along those lines?
Yeah, it is. Well, first of all, the definition of small is kind of brings a smile to my face because, 300 megawatts is bigger than most of the reactors that I worked on in the UK. So not small by any means. A 300 megawatt it's just a number that has been agreed on as that's what small means. Rolls-Royce, for example, has a small modular reactor, but it's 470 megawatts.
Wow.
So it's hardly what I would call small. I mean, Pickering Generating Station in Ontario, their reactors are 500 megawatts electrical output, 540 less internal use, but 500 megawatts is what they put out to the grid. So, the Rolls-Royce reactors are certainly not what I would call small. They're small compared with the EBRs, the French reactors, the big ones, which are 1600 megawatts. So I suppose from that point of view, they're small, but it's still an awful lot of energy. They are more, their use is that you can add them incrementally to the grid. That's the big advantage. So, they're factory made. That's the big thing. They're not assembled on site. Like big reactors have huge amount of construction infrastructure you've got to put together. A lot of concrete pouring. These reactors haven't got any of that. Most of the shit, they're underground for the most part. Not all designs like that, but the majority of them use the ground as the shielding. So you don't need as much concrete around them. So the major advantages in using SMRs, and there are many different designs. GE Hitachi has a design that is a boiling water type reactor, similar to the big boiling water reactors, except it's smaller, more compact. But same general principle. You boil the water in the core and the steam goes straight to the turbine. So with a PWR, you've got an intermediate component, which is a heat exchanger, boiler, to transfer the heat to the water to make steam. So you got it a little bit more complicated with the PWR. But very simple designs. I mean, the PWR reactors from GE Hitachi have very few components. I mean, there's the reactor, which boils the water just like a big kettle and sends it straight into the steam turbine. So no intermediate pipes or anything like that. So they're very compact. The big thing is you can put them on a flatbed truck, move them about. That's the big advantage. They're much more easily movable. The big components for most of the large reactors, you have to move around on a barge or heavy duty equipment to move them about. With these reactors, that's not the case. You can build them in incrementally, so you can add 300 megawatts or so. If you want another 300 megawatts, it should take 2 or 3 years to put one together. So, but the big thing is they're factory made and under controlled conditions in the factory, which means you get higher quality, less time taken, mass production, all of the advantages of factory assembly. And those are huge in the nuclear industry. The more you can make things the same in a production line type environment, the cheaper they're going to be to make. And that's the promise. We haven't seen that yet because we haven't made a series of them. Rolls-Royce is gearing up to do that in the UK. They have plans to build, I think, 20 of these. So we'll see if that does actually reduce the cost. Jury's out on that. I think they will. It's like, cost you, $1 billion to build one Ford car. It costs you, 30,000 to build 1 million of them. That's the difference. And that's the promise of mass producing small modular reactors.
How far away in the future is that, do you think?
It's right now. Darlington station near where I am is building a small modular reactor right now. They just started construction of it. It's a
But
GE Hitachi unit.
right, I also saw that GE Hitachi has already submitted the GDA, I guess it's called, for its 300 megawatt reactors to the UK government.
Yes, they
So
have.
yeah, so it's something that's going to be what is this going to be like? It's going to be part of the is it going to be part of the energy mix? Is it going to replace something? How do I look at it as I guess as an investor in uranium? Does it do something for me? Does it do something to me? How do I look at it?
Hmm, that's a good question. Well, I mean, they all use uranium, right?
Hmm.
Uh, how efficient they are at burning uranium is probably not that much different to a big power reactor. They need a little bit higher enrichment, so I'm told. So that makes them means they use a little bit more uranium than would otherwise be the case. But it depends a lot on the design. Some of them, for example, the true small modular reactors are really small, like they're 15 megawatts or so, and they're designed for you refuel them once, or you put fuel in them once, you ship them up to a remote mine site, or in northern Canada, or wherever in the Arctic, and you run them for 20 years, no fueling, don't need operators. You just sit there. They produce heat and electricity. Probably one or two operators to look after them, but not very many. So there's that type of small modular reactor, and that market is very different to the grid market. That is going after, a lot of these northern communities use diesel, and that's expensive. You got to truck this stuff up, 1,000 miles to northern Ontario, say, and over ice roads because you can't get in there during the summer, and you can't fly this stuff in. There aren't airfields up there that are big enough to handle big air tankers, so you have to bring it in by road. And the only way you can do that is in ice roads when the ground is frozen, and you can move trucks across it. So that's the market that the very small modular reactors are going after. A lot of remote mining communities, gold mines, and the like. Have small power requirements. 15 megawatts would be quite large for a mine site, I think. So, but it's ideal for that application because it can produce heat and it can produce electricity, and you don't have to worry about fueling it for 20 years. And when the 20 years is up, if the mine's still running, you take it out, put a new one in, and that you can bring them in on a flatbed. They're that small. So there's that type of small modular reactor. And again, they all use uranium. Not one of them runs without uranium. So the more of these you add in different markets, then the more uranium is going to be required. For big industrial sites, Poland is looking at building small modular reactors for some of its big chemical processing plants. And they've signed an agreement. I think it's with Westinghouse. Westinghouse has a small modular design. It's pressurized water reactor. It's based on a pressurized water reactor. But what they're looking at is running big industrial complexes using small modular reactors because they can produce heat and they can produce electricity. Right now, we use reactors to produce electricity, not so much on the heat side of it, although China's just set up a district heating scheme using a reactor. So they're actually heating houses with the waste heat from the reactor, which is very clever. So, how much is it going to reduce uranium demand? No, it's going to increase it. How much it'll increase it, that depends on how much market penetration they get, and whether and it's looking very promising. There are a lot of industries that want stable electricity prices and stable energy prices. German industry right now is suffering mightily because of the gas business with Russia. BASF just announced that they cannot produce ammonia. It's cheaper for them to import ammonia into Germany than it is to make it. So that's because their energy prices are so high. So a lot of European nations are looking towards small modular reactors, not Germany, I might add, but Poland and Czech Republic and Romania are all looking towards small modular reactors, not just for their power grid, but also for their industrial base. So they don't have to burn so much gas. And they're reliable. I mean, nuclear power stations go on forever.
Sure. What are some of the issues with them then? Because all you said so far, I think sounds, pretty promising. It's here, it's now, it could help a lot of people. I guess you could start talking about Africa as well, but what are some of the issues here?
The designs haven't been tested in real life yet. It's my experience is it's one thing to design something. It's a whole other set of issues to operate them successfully. There are always things that you can't simulate or don't know about. That's why my preference, and I think the reason why our local industry here, Ontario Power Generation, has gone for the GE Hitachi design, is it's proven technology. They know BWRs very well, so there's not a lot of new stuff that needs to be found out. There's not, we know the metallurgical issues with them. We know how they operate. It's not going to be that much different if you just condense the design down. But there's always the what ifs, this is new technology using old technology. It's a very much smaller design than the reactors that are currently operating. Browns Ferry is a boiling water reactor in the States. It's 1,100 megawatts, I think that plant is. So, that's they've made that reactor a lot smaller than the one that's in Browns Ferry. So 300 megawatts. I mean, it's only about 4 or 5 feet diameter, something like that. 6 feet, very, very small diameter. So are there unknowns? There are always unknowns. It's not new technology from the point of view that we haven't used BWRs and PWRs before. We have, but the design to condense them into a small space is new. So we'll see how they operate. I think they'll be very successful, is my view. GE Hitachi know their business, and I'm sure they're going to be successful in promoting that, as will Rolls-Royce. They've been building PWRs to ships for years. They know this technology. So there's the SMRs that use existing technology, and there's SMRs that use new technology. And those are the molten salt reactors and the fast reactors. It's not that that's particularly new technology. It has been used before. There was a molten salt reactor at Oak Ridges in the States. It's a big research lab down there. So, sure, that the physics of it is fairly well known. The actual operation of them over long periods of time isn't. So, I would say the level of unknowns goes up the less you've used a technology, as a general rule anyway. We've used BWR technology and PWR technology a lot over the years. We've got 50 odd years of experience using it. Molten salt reactor technology hasn't had that length of experience. So there may be things that we'll find out as we operate them. But, they have different advantages. Molten salt reactors can store energy in the form of molten salt, which is something a regular reactor cannot do. So they have they'll be used in different facets of the market going forward, I think, is the way you will see things develop. So the existing technologies like PWRs and BWRs, you'll see those used on the power grid because we know them. The other technologies, I think, will be used in industrial sites where they have a requirement for heat and electricity because they can do both. And some of them, as you mentioned earlier, some of them can actually use used fuel. So should we ever get into a situation where we've got no uranium left, then sure, these would be the ideal thing. But it's early days yet. As a uranium investor, is it going to make the situation with uranium better or worse? They all use uranium. So, they're going to consume uranium. So it's just an additional consumer. How successful they are in the market is how much uranium they'll consume over the years. Don't know that yet.
How much uranium do they consume? Like if you look at a standard, 1,000 megawatt reactor versus the GE Hitachi one, which is 300 megawatts, the small, as you call it, quote unquote small, does a regular reactor just use 3 times as much fuel? Is that just as simple as that?
It's more or less that, yeah. It's not exactly that, but my understanding of them is they use higher enrichment fuels because they can run for longer with the higher enrichment. So they may refuel every 18 months. Some of the designs, you don't need to refuel them at all, which is quite amazing. But with the ones that I've seen, you'll be refueling them about once every 18 months, just as you do a regular BWR. And will they use more uranium? I'd say marginally they'll use a little bit more per megawatt.
So those are not the reactors that use the high assay low enriched uranium, HALEU or whatever you call it. So because you see, the U.S. government testing, down blending warheads for some of these potentials, or signing contracts to make more of this high assay low enriched uranium. Which reactors use those?
That's the TerraPower reactor that Bill Gates is involved in. There are other reactors that need it as well, but that's the main one. The problem is that the US doesn't have a manufacturing plant that can make this fuel. It's all made by a Russian company called Tenex. So that's the issue right now. In fact, you may have seen on the news that they deferred the installation date of the TerraPower reactor by 2 years because they didn't want to use Russian helium. But the US government knows that, and they're building a plant to make this stuff.
Okay. Are you investing in any of these technologies, any of the producers of the fuel, some of the plants that are being built there? Because you have also NuScale, I guess their ticker symbol was SMR. So I've never looked into it. I probably should have, but are you interested in any of those?
No, I'm a pure uranium investor. Anything that uses uranium is just a user, as far as I'm concerned. Are there? NuScale is probably the one that has the most promise. Early days yet. For myself, I can only speak for myself. I wouldn't put money into them just yet, but when things start to move, the whole world view of nuclear power is changing, which is something that's unique in my lifetime. To have so much positive news about nuclear power. It's all been negative over the years. Anti-nuclear people seem to have, cornered the airwaves. But now I think governments particularly are realizing that, they can't be dependent on other countries for their energy supply. That's the big thing that's come out of this Ukraine-Russia conflict, is that, if you base your whole economy on somebody else's energy supply, if you have a falling out, well, they're going to cut you off, and they have. You noticed a big sea change in Japan recently with the new government they've got there, has done a complete 180 degrees and is now, promoting nuclear power like it's the best thing since sliced bread, because they have no fuel. They have no fossil fuels. So they are entirely dependent for all of their economy on the suppliers of oil and natural gas. And if somebody says, well, we're not going to supply you anymore, then Japan shuts down, and they can't afford that. That's why they built nuclear in the first place. That was the very reason for doing it. And after Fukushima, they kind of lost that idea and forgot about the fact that they don't have any fossil fuels of their own. Now they're having to import liquid natural gas and oil and coal and everything else to keep the lights on. And that's not so good for the environment. So, they have done a complete 180. So has South Korea, complete 180. So has Sweden even, which really surprised me, is that they're going back to nuclear power in a big way. Wanted to build new reactors now. Never thought I'd hear that in my lifetime, but here we are. The technology of SMRs, although some of it's well known, there are always going to be technological problems that come up. I would be astonished if we don't have that with small modular reactors. So I would, great that these companies exist. Would I bet my pension plan on it? No, I would not want to do that, I think, at this stage. But it's like any investment. If you get in early, that's where the big gains are. But there's a risk to that. It's like uranium mining. So no, I don't have any investments in SMRs. I have been looking at them. There's certainly some appeal there for me as an investor as well. But I'm just a little bit cautious at the moment. It's too early.
What about other nuclear related technologies like enrichment? You have the laser enricher, for example, Silex. Conversion seems to be a big issue. I don't know if there's an option to invest there, but there are interesting publicly listed companies that service the nuclear industry, if you will. So you're staying away from those because you said you're all uranium. Is that a choice, or why don't you want to be in them?
Risk. Risk is the main thing. You can't predict politics, and uranium to me is a supply and demand issue. It's some will disagree with me. Having a conversation on Twitter this morning about this very subject, but it's a supply and demand as far as I can see it. There isn't enough mine supply to meet the demand, and that's a simple equation I can understand. So I can understand uranium mining and uranium supply. What I can't understand is the politics between Russia and the West. And if, for example, you invested in, say, Urenco to make your enriched fuel, right now everybody's moving away from Russia because of the conflict. But in 10 years' time, will that still be the case? I don't know, and I find it very hard to predict that, because if you do make that investment and all of a sudden Russia, comes back into the fold again, so to speak, politically, then all of a sudden you've got this huge capacity back on the market again. I can't predict that. That's really uncertain for me to do that, and I wouldn't. And that's the reason. It's nothing to do with whether they're good investments or not. It's again about supply and demand. There's only an artificial supply problem because of Russia. It's not a real supply problem, right? There's no problem with uranium enrichment or HALEU fuel or anything else if you include Russia in the picture. They're one of the biggest enrichers, they're the biggest converters, and they're the biggest producers, the only producers of HALEU fuel. If the Ukraine conflict didn't exist, we wouldn't have a problem. There'd be no issue with buying the fuel from Tenex, and there would be no issue with buying enriched fuel from Russia. But now there is. But that's a political thing. That's not a supply-demand thing. A big difference between the two, in my view.
What about something else that you think I might be missing being outside of the industry? Is there something interesting happening with technologies that we didn't talk about? Is there something else happening in, I don't know, in the supply and demand side? Whatever, something that I might be missing.
I think there's a bit of a disillusionment going on in the political circles with wind and solar. There is, apart from what's going on in Germany, I mean, it's a bit of a fiasco. if you look at it from an energy point of view, they're now the worst polluter in Europe, and they've just shut down all of their least polluting power plants, which is nuclear, for ideological reasons. The perfectly safe plants have been run for years, and Kraftwerk Union that built them is one of the best constructors in the world, in my view. Superb engineering that went into those plants. But they've decided from an ideological point of view to shut them down. So now Germany has an energy crisis. It's self-inflicted. They created this themselves. It's not just because of Nord Stream, shutting down Nord Stream. It's because they shut down their major supply of baseload carbon-free electricity and went for wind, which needs gas, and now they've got to burn coal. And they don't have a lot of coal. They've only got dirty coal. So I think, when a major industrial economy like Germany shows that wind and solar really don't cut it, I think it sends shockwaves through the rest of the political community that, oops, maybe we better not go down that path. And that's, if you look at every jurisdiction that has high amounts of wind and solar, their electricity prices are enormous. They're much, much higher than everybody else. So I think that political climate is changing. And of course, people don't want to build coal stations. They don't want to burn gas. Well, there's only one alternative left, and that's nuclear. And you've either got to, decide whether you want to build them or not. But what's happening now throughout the world is that people are deciding that this is the way they want to go. Even Bangladesh has 2 nuclear plants under construction, big ones, built by Russia, might add. But, those countries, that's how they're going to grow their economy. Electricity prices in the UK have just gone through the roof. They're ridiculously expensive. Yeah. And it's largely because of wind and solar and mismanagement of their electricity system. Yeah. A lot of the older nuclear plants have shut down in the UK, because they reach the end of their life, as they do. Components don't work anymore. So that's the big backdrop to the uranium story that people need to understand, is that the world is moving heavily to nuclear power, not just in a small way, but in a very big way. And that won't impact uranium prices yet, but down the road it is going to, has to.
It has to, but it's something that will happen in the future, I guess. For now, what I'm seeing in terms of the uranium equities prices, at least, they're mostly impacted by whatever's happening in the financial markets, risk on, risk off. But sure. I hope it's going to change. I hope they're going to start following the fundamentals, I guess. But
it's associated with what I just talked about. The amount of contracting that's gone on, long-term contract. I don't look at spot price. People keep going on about the spot price, this, that, and the other. It's a very thinly traded market. Most of the uranium is sold on long-term contracts. In fact, nearly all of it is sold that way. So to say that this side market called the spot market is going to somehow disrupt long-term contracting is neither here nor there. It's not. What has happened is that long-term contracting has not been occurring because spot market availability was very high due to underfeeding. People wanted to get rid of their stored uranium, the Fukushima, all of that created a glut of supply. So the spot market was the place to go. You wouldn't want to lock yourself into a long-term contract when you can get it dirt cheap on the spot market. That's changed. Nobody's underfeeding anymore. It's gone the other way. They're overfeeding to get the enrichment levels they need, because UF6 is in short supply. So what you've seen is a huge uptick in the price of UF6 conversion and in enrichment. And sooner or later that translates into U3O8 demand. It has to. The physics tell you that it has to happen that way. So what has happened now is that the bigger mines like MacArthur River, Cigar Lake, and the ISL facilities in Kazakhstan. Kazakhstan used to sell on the spot market. That was one of the reasons that spot market price was so low and the availability was so high. Kazakhs are not doing that anymore. they set up a trading arm in Switzerland to sell on long-term contracts. So Kazakhstan has moved from this spot market sales to long-term contracts. So, and they're doing long-term contracts with the Chinese, particularly, and with Russia. Russia doesn't have a lot of uranium. Kazakhstan's right on the border. It does. So they're getting the uranium from Kazakhstan. So a lot of companies, the big players like Cameco and Kazatomprom, those people are now long-term contract. Cameco's always been that way. It's always sold on LTCs. Not so much Kazakhstan or Kazatomprom. So what's happening now is that the utilities can't get the long-term guaranteed supplies that they need from the spot market. So they've gone back to long-term contracting. So let's take Cameco because it's the best example. They have two major mines, McArthur River and Cigar Lake, and they've also got Yeelirrie in Australia, Western Australia. But those are the two big ones. Those mines have about 10 years of life left, and they're their lowest cost producers. So they're their tier one assets, is the term that Grant Isaac uses, and all of the board of directors of Cameco. That's the cheapest. What they mean by tier one is it's the cheapest producers. So each mine has a different cost to it. So the price of uranium that comes out of McArthur River is not the same as the price that comes out of Cigar Lake for a variety of different reasons. So once you've contracted the remaining life of Cigar Lake and the remaining life of McArthur River, you've then got to go to a different set of assets, which are the tier two assets, which are the in situ leaching facilities in Wyoming and what do they call it? Crowbutt, and what's the other one? Can't remember. Anyway, they have in situ leaching, but they're higher priced. They cost more than Cigar Lake does to produce. So when they contract those mines, the price is going to go up. So the long-term contract price will start to increase as they use up all of the existing mine capability. And of course, what happens when there is no mine capability left, which is where we're headed? There isn't enough uranium being mined to meet the current demand, let alone future demand. Forget SMRs, they're not even part of that picture yet. So when all of this new demand starts to come on, utilities that operate them are going to have to go where to get their supplies. There's only the spot market left, or yellow cake and the financial people that have stockpiled it over the years. So that's where we're headed. So once the long-term contracting has used up or has contracted out all of the existing mine supply, there's none left. If you want uranium, there's only one place to get it, and that's spot market. So people have it backwards. It's not the spot market that drives long-term contracting. It's long-term contracting that drives the spot market. So exactly what happened before. Mm-hmm. And the reason why it happened before was McArthur River and Cigar Lake flooded. So they had contracts, but they couldn't meet the contracts. So people had to go to the spot market to get their supplies.
All right. Right. I think I'm all out of questions. I think I'm going to let you have your holidays in peace without having to look at my face. What do you think we should talk about next time? I mean, I'm just assuming you want to come back, of course. But so if you would want to come back, what do you think we should talk about next time?
I'd like to talk a little bit more about these molten salt reactors because they're very interesting. They affect both the supply and the demand for uranium. There's none actually being built yet. There's a lot of research going on with them, and there is a company in New Brunswick that's planning to build one there, a demonstration plant. So I'd like to talk a little bit more about those, and because some of those can actually burn used fuel, which is what we talked about earlier. But those interest me quite a lot. I think they may have an impact down the road, not yet. But yeah, maybe talk about some of the miners and what they're up to. That's really what I like to look at. I don't look at, like I said, in many posts on Twitter. I don't really follow the equities that much. To me, the value is in what the companies are doing, how they're going to add future value to their enterprise. Companies like NextGen will open up Arrow in the next few years. Fission 3 looks like they found a really good deposit. Maybe talk about some of the equities a little bit, and see what they're doing. And I do have stocks in nearly all of them. I think a few that I don't.
Okay.
That's a disclaimer up front. Not promoting anybody, but I can tell you the reasons why I'm invested in some of them.
I think that'd be interesting. It'd definitely be interesting, especially for me. Well, thank you. Thanks a lot for coming on. Thank you for investing so much time in me, and I really do appreciate you. I think I've learned a lot. I've taken a lot of notes, so I'm gonna have to walk through them, and also while editing the video, that's actually a benefit for me because I get to be in the conversation, but then I also get to edit the video, and so I can hear it twice or 3 times at times. So it's been good. Thanks a lot for being here.
So, it's a very technical business. And what you've got to understand is how those technicalities of the business affect the uranium scenario. That I think a lot of people are missing. It's like everybody's saying fusion is round the corner. I know that it isn't. I know people that work on it. It's a very difficult scientific problem to solve, and I would never put anybody down. I mean, what they just achieved is a fantastic achievement. Really is. But when investors see that and then they think, oh, uranium's not going to be used in the next 5 years, that's not so. You have to put it in context, and hopefully that's what I can do for investors, is to help them understand how this technical stuff fits in with this investment thesis. Because people jump to too many conclusions and lack patience. It's a long-term business, and it requires a lot of patience. It's the weirdest commodity ever. Uranium is nothing like any other commodity. It is not like copper. It is not like iron ore. It is completely different to all of them, and it's a very opaque business. I had an argument with one guy. I had to block him because he was being quite rude. But he's basically saying that the spot market is the thing to watch, and it really isn't.
I sure agree with you. It's definitely an opaque market, and I am a lot of people. I jump to conclusions. I make assumptions. That's why I got it wrong, and that's why I didn't. I guess if I had known that it was sort of a momentum play, I would have at least taken some profits, like some people did. Generally when the what am I looking for here? The sentiment, when the sentiment was almost at mania levels, at the highs last year, some people like Lobo Tigre, they were taking profits because they knew this was a risk on play. It was a momentum play. And the uranium markets has offered a lot of these opportunities to take profits and rebuy at lower levels. That's not being me. I was jumping to conclusions. I was expecting that the stocks would decouple based on the fundamentals, because I understand that the fundamentals are good, but I think I jumped to the conclusion that supply shortage, let's just buy it because the price is going to go up and all these things. And conversations like these really do help me wrap my head around it and maybe not make the same mistake again. So
I'm not a trader. I don't go in and out of stocks. I just buy stocks that I believe are going to do well, for a lot of different reasons, not just because of the uranium situation. But for example, I have quite a chunk of NextGen, which I bought at 60 cents. So, that has been well over $6. So it's 1,000% gain for me. So, but I bought that a long time ago. Why did I buy it? Because when they first drilled Arrow, the count rate was over 20,000 counts per second. It could be thorium. It's more than likely uranium. Did I take a gamble? Yeah, I did. And it was uranium, and it's now the biggest, most productive, or the biggest future mine in the world. And somebody said to me the other day that when Arrow is running, it will produce on its own, that one mine, more uranium than Cameco produces in all of its mines. I haven't actually checked that calculation, but it was from a pretty reliable source. So I'm inclined to believe it. I should do that, actually run the numbers. But the other thing I was trying to get at, and one of the reasons I had a bit of an argument there on Twitter, was people, they keep saying, oh, long-term contracts are this price, that price, and the other price. And the market is opaque because Cameco does not publish that information. That's commercially sensitive data. There's no way. And I've seen some of these contracts. They're books that thick. Huge amount of information. And it's not just about U3O8 prices. It's about the whole fuel cycle, because utilities don't want uranium. They want fuel elements. Finished fuel elements is what goes in a reactor. Don't shovel yellow cake into a reactor. You put fuel elements in there. And between the U3O8 and getting all the way to the fuel element is a complex process with a lot of players involved. And Cameco does some of those steps, but not all of those steps. It does all of those steps for some utilities. In CANDUs, it produces the entire fuel cycle, digs the uranium out the ground, makes the UF6, uranium dioxide. It doesn't have to enrich because CANDUs don't need that. But when people tell me, that what the long-term contract price is, I mean, that's just bullshit. Not even most of the people in Cameco don't know that. Only a few people write those contracts with the fuel buyers for the utilities. Plus, it's commercially sensitive, not just for Cameco, but it's commercially sensitive to the utility as well. They're not about to release all of that technical detail to everybody because they'll know what a good deal they got. You just don't do that. It's a commercially sensitive document. So it's opaque. UXC does kind of put out some data, but I'm not sure how accurate it actually is. But those contracts have a lot of elements to them. It's not only the U3O8 price, it's also where you store it, how you store it, how long you store it, how long this contract's for, where you want it delivered, what form you want it delivered. It's a shopping list of stuff, and every utility has different requirements, and those long-term contracts have different dollar values depending on those requirements. So, for somebody to go on Twitter and say, long-term contracts, they know the price, they don't. Nobody knows. So, and that makes it very opaque. If you go on the Chicago Mercantile Exchange, you can buy anything. You can buy pork bellies, you can buy orange juice, you can buy this, that, and the other. The one thing you can't buy there is uranium, because it's a regulated product, and it's very strictly regulated. Because if you could buy it on the Chicago Mercantile Exchange, you could buy all the material you need to make a weapon. So the government's regulated, and it's not sold that way. It's done under LTCs, and it'll always be that way, either there or the spot market. But in terms of the amount sold, long-term contracts is here. Spot market is way down here. Tiny, tiny part of the market, very thinly traded. It's been a bit distorted over the years, but because of the Fukushima, utilities were selling material back into the uranium market, into the spot market to make money, recoup some of their losses. TEPCO particularly, Tokyo Electric Power. Don't know that for sure because they don't divulge that information, but it's pretty certain it was one of those big utilities in Japan. Are they going to be doing that now? I doubt it. If they're going to be starting up all these reactors, they're not going to be selling uranium again. Don't have any. They have to buy it from somebody. So that's part of it. I think people misunderstand uranium pricing and how it's priced, and it's a very complicated business, not just something you can put in 50 characters on a Twitter blurb. So going by spot price is really not the way to look at it. You've got to look at the amount of pounds that Cameco and the others are selling in comparison to the capacity of the mines to produce it. That's the number to look for. And once Cigar Lake is contracted out and MacArthur River is contracted out, Cameco is not going to be selling on the spot market. It's probably going to be buying on the spot market, if anything.
And that number grew substantially this year, if I'm not mistaken. So I imagine if it was, I imagine that if this year was a good year for equities overall, for risk on in the markets in general, and if this was happening, what happened this year for uranium for nuclear fundamentally, if it all had happened in, let's say, 2017 or 2019 before the virus or whatever, the stocks would have been out of control. I think they would have outperformed the broad markets.
I believe you're right. This is an aberration. And I think what's going to happen is when the interest rates start to stabilize and, the market recovers, as it always does, people will be moving back into the uranium market right at the time when there is a genuine uranium shortage. That's why I think, I've been asked this question many times, do you think uranium will exceed what it did before? Will it go above $200 a pound? Very likely, I think it will. If you just add inflation to $137 a pound since 2008, you get over $200 a pound uranium. Just inflation added to that. If you do compound, if you work out 137 and do 2 or 3% compound interest to now, you get well over $200 a pound. So all we've got to have is a repeat of last time, and you're there already. Some people think that the demand will go down, but again, uranium's not like any other commodity. It's completely inelastic. People don't shut down nuclear power stations because they haven't got enough uranium. They'll pay whatever it takes to get it.
Right. That's also a common misconception that I see out there. People saying, once uranium is that price, what are they gonna do? They're gonna this $6 or $10 billion asset, they're just gonna shut it down because it costs them a little bit more to run it. Doesn't make sense.
The biggest costs are not fuel. I've worked in nuclear power stations my whole life. The biggest costs are not fuel. The biggest costs are labor and capital costs. It's so if you sunk, let's take the UAE for example. I mean, that's the best example I can use. It's the cleanest example. They just spent $24.5 billion US on 4 nuclear power plants. If the fuel, which is about 5% of their costs, doubles to 10% of their costs, are they going to shut down 25% of their grid electricity capacity because of a little bit of fuel? That's not going to happen. The biggest cost is capital expenditure. That's what costs you the money. And if you're not running the plant, then you have got no money coming in. Right? You just got a big pile of concrete sitting out in the desert somewhere because it's not producing you anything. It's got to be running to make money, and in order to run it, you need uranium, and you're going to pay whatever price uranium is to do that. Plus, it's not just the U3O8, right? The U3O8 is a small part of the fuel. The biggest costs are converting it into UF6 and enriching it, enrichment being by far the biggest cost. And then once you've done all that, you've got to convert it back into uranium dioxide. You've got to make the pellets. You've got to make the fuel elements. That's the cost. the U3O8 bit of that is very, very small, probably less than 10. To be conservative, 15% of the cost of the fuel is the actual U3O8. So it's not the whole cost of the fuel that doubles. It's the 15% of the cost of the fuel that doubles. Not the same thing at all. So people have got to get out of this idea that what goes into a reactor is U3O8. It's not. A whole lot more stuff goes into it than just that.
No, that's how I learned it. It's just yellow cake goes into the reactor, green goo comes out of the other way and goes into the lake, and that's it.
Yeah, that's the Homer Simpson way.
Yeah. Malcolm, this has been great. Thanks so much for putting so much time in me, and I'm looking forward to our next discussion.
I enjoy it. It's really good.